Application of definite integrals. Area under a curve. Which is a little bit different than just the definite integral, because area under a curve is defined as the area. Sometimes we do area between a curve and the x-axis, and we've already learned that any area that's underneath the x-axis shows up as negative. So you get questions like this. Find the area enclosed by the line y equals 2x minus 1, the x-axis, and the lines x equals 1 and x equals 5, and make a sketch. So we can easily graph 2x minus 1. On this graph, you could label x equals 1 and x equals 5. And what we're finding is that yellow area underneath that curve. So what does that mean? That means we're finding the definite integral from 1 to 5 of 2x minus 1 dx. Now, for this one, since it's a straight line, could you see that you could do this other ways? Like, I would probably go make a rectangle here, find that area, and then you have your area of a triangle formula, add those two things together, you'd find your area, okay? Which wouldn't be super hard, but finding the integral of this one also is not super hard. Working backwards, you'll get x squared minus x. And so with the definite integral, remember, we put the square brackets around it. We go from 1 to 5, and then you plug in 5 and plug in 1 and subtract, and you get an area of 20. So all things considering, even though you could calculate this with your regular formulas, this is still almost faster than that. And the powerful thing about this is it doesn't have to be a nice straight line for us to figure out that area. So if we look at the next one, everybody done here? Now this is the curve that we're looking at. 15 minus 2x squared. It would be a parabola opening down. And we're finding it between negative 2 and 2. And so setting that up as a definite integral, you write your integral sign going from negative 2 to 2. And this one we would have no formula that we could solve it any other way. Yes? Yeah, we always go, well, you don't have to have the bigger number up on top, but when we're doing the area between a curve, you're going from left to right. You'll put minus 2 on the bottom, 2 on the top. Integrating this isn't bad. It's just your regular power rule. And then it's just a matter of plugging things in. And the rest of the calculations would be fairly easy, just time consuming. So I'll get you to try example 3 on your own. We have a long time where it's just staying on the same thing. How did your graph look? It's moved up 1 from 0 to pi would look like this area. And really cool that its area is exactly pi. So you're only figuring up to this part, right?
Yeah, I drew my scale wrong.
Yeah. You made your period pi instead of period of 2 pi. So now each of the three examples that we did all had the areas between the curve and the x-axis. The notes in the next little section here say that sometimes you get a negative number. Okay? So if a function is below the x-axis over an interval, then the definite integral would give a negative number. The negative sign just indicates that the area is under the x-axis, not an actual negative area. So if you wanted to find its actual area between it and the x-axis, all you'd have to do is take the absolute value of that. You could either take the absolute value of just the section that's below, or you could take the absolute value of the inside of the function, because that would flip it above the x-axis as well. Usually what we do is we find the place where it is equal to 0, where it switches from positive to negative, and split your integral up by those x-intercepts. So if you have to find the area between the curve and the x-axis, you'll need to find all the x-intercepts. Separate those integrals, solve each integral separately, and then make the negative ones positive. And you could do that by adding absolute values to all the negative areas. So here's our first example. And when we look at the graph of x squared plus 4x, between negative 2 and 0, it's all negative. So when we find this integral, our answer should be negative as a result. Set it up, go from negative 2 to 0. I already put absolute value bars around it because I know the answer is going to be negative. Now sometimes you'll do the math and you won't know an area is going to be negative until you get the answer is negative. And then you sort of work backwards and like, oh, I'll add my absolute value bars the way back so it looks like I knew the whole time. Not a hard integral. And you get negative 16/3 for that section. So the actual area is positive 16/3. Now, as far as writing things down, I know you can plug in the numbers and get the values. So you might want to plug them in and then just write the answer, because it would just be a matter of simplifying that from there. So now we're looking at the same curve, but we're going from -2 to 2. So here, our x-intercept comes into play. So if we wanted to find the area, we would break it up and do the area from -2 to 0, and this is what we already solved for, and then do the integral from 0 to 2. Here, I'll scroll it up for you as well. Yes? Well, okay, almost, but not quite, okay? So the question is, can we do this? And the answer to that is no. Because if you did the inside first, the positives and negatives would cancel each other out already. Okay? We already know that the yellow is 16/3. Here, we'll put the answers up here. The yellow we already knew was 16/3. The green is 32/3. So if you did this right away, the inside would come out to be 16/3, and then the absolute value would keep at 16/3. However, if you did this, oh, that's what you were trying to say? Okay. Yes, you could do that. The only problem is by hand, how do you do the integral if you have a calculator and you're not doing it algebraically, right? But again, that won't be allowed in any university class. In university class, you're going to have to do it by hand, so that's why you'd have to separate it. So taking away these absolute value bars and adding the absolute value bars inside, for sure, if you have a calculator, that would work. Because what that would do is that would take this section here and flip it over, and then your area would both be positive and work out perfectly. Cool, eh? But for our sake, what we're going to do is we're setting yourselves up to do well in university. To do well in university, you have to do it by hand. So you're going to need to find that x-intercept, split up your integral, and make the negative section positive. So I'd like you to try the next one on your own. You'll have to find the x-intercepts, draw a sketch of that graph, find out which sections are negative, which sections are positive. Do you remember how to graph that from grade 12?
Yes.
Find your x-intercepts. Yeah, you just did it, eh? It's finally catching up. Is this your eraser? No, eraser, no. There's your x-intercepts, right? So 0, 1, and 2. And it's x cubed, so that means starts down here, ends up here. No, no problem. Very nice. So I'll put the graph up to see if you got the graph right and the factoring. Set it equal to 0. You could factor out a common factor of x. So you have x-intercepts at 0, 1, and 2. 0, 1, and 2. And then as far as the integration, the yellow and the blue parts will be positive. The green section is going to be negative. And what I wrote here, because I was lazy a little bit, is instead of writing the whole function every time, I just decided to write the letter y, because that's what it's equal to, instead of all the x's.
I was even lazier. I didn't write any letters.
You didn't write anything.
I just wrote the integral sign and numbers.
And then, trust me, I calculated each of these areas. It's going to be 1/4 plus 1/4 plus 2.25. I'm sure you could get it. But we're going to take 10 minutes to work on the questions at the bottom. So take out your textbooks.